West, we work there quite regularly. Right. As I said, this is not what I planned. When I started looking at this, I found how little I actually knew and understood about CO2 emissions, where they come from, where we sit currently in the world, and what we've got to do to get them back down to zero. I haven't even gone into why we need to do that. I hope everyone understands why we need to do it. So I haven't really gone into that. But this is less about temporary works, and this is more about the net zero journey overall, rather than what we can specifically do about it as temporary works engineers. So the starting point is understanding current CO2 emissions. So there's lots of data out there. The best data I found was from our World in Data, which has got more graphs than I've ever seen before in my life, of all sorts of different aspects of life on Earth, I suppose, including a very large section on CO2 emissions. Now, the first question I had was, are we talking US billions or UK billions? Because they're quite different. One is a million and one is 1,000 million. We are talking US billions, so 1,000 million is 1 billion. So the current annual CO2 emissions is around 34 billion tons of CO2 per year currently. Then there's also the next question that comes up is, are we talking metric tons or American tons? Again, doesn't seem much of a difference between a US ton and a British long ton and a metric tonne. But when you're talking about 34 billion tons, it makes one hell of a difference. If we're talking a 16 kilo error, i.e. between a long ton and a metric ton, then that equates to 500 million tons of CO2. So it's quite important that we get our units right. And from everything I've seen and managed to track down, I think it is metric tons we're talking here. So that's kind of set the scene. Right, there's lots and lots and lots of data available. I haven't paid for any of this data. This is all stuff that you can go out there and find and have a look at for yourself. I haven't tried to validate it other than a sense check, which is by cross-checking with other data and making sure the numbers seem around the ballpark. Tried to stick to legitimate sources. So for UK, that's been the ONS, Office of National Statistics, and government websites, and people who use that to produce infographics. The next question we come to is CO2 emissions or equivalent CO2 emissions. So CO2 would be direct CO2 output. So if you burn a fossil fuel, that will give CO2 off. We also have CO2 equivalent, which takes into account other greenhouse gases, and as a way to try and compare and understand it, they have put an equivalent together. So instead of talking about CO2, methane, blah, 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 it's all made into an equivalent CO2. I've tried to stick to pure CO2 emissions because it keeps the numbers all consistent. And then the next question you come to is, are we talking about production-based, i.e. within a country's border, or are we talking global CO2 emissions? So what I mean by that is, as a country, the UK imports a lot of materials. So if you only consider the CO2 within our borders, you get quite a different answer to if you consider the CO2 that's produced on our behalf. So looking at this chart here, you got the red line's consumption-based and the blue line is emissions-based. So that consumption-based takes into account stuff that's manufactured on our behalf outside of our borders. So it's a factor of about 1.4, depending on what figures you use. It's somewhere between 1.3 and 1.4 times our emissions within our borders. But this is a point I come back to time and time again when we're going through this. But there's a lot of things, and this is where this is why my presentation has changed tactics, understanding all of this and what it actually means and how we deal with it. So again, quite a scary graph here. Over 35 billion tons of CO2 emissions. That's just from fossil fuels, so that's not equivalent. That is CO2 emissions from burning fossil fuels. There are some significant things that need to change to get us to net zero, as you can probably appreciate just from looking at that graph. So the other one, that's emissions per year by world region. Cumulative CO2 emissions is also a very interesting one to look at. So this shows since 1750, the CO2 emissions by country, as I've done it here, and then this one's by geographic region. And interestingly, United States is still way out in front in terms of cumulative CO2 emissions. If you go back to the amount they're producing now, they're nowhere near as big as China or Asia as a whole, but cumulatively, they are still, what are we talking, 150, maybe 200 billion tons in front of China in terms of the amount of CO2 they've dished out over the years. When you look at it on almost a geographic, so by the continents, it's very, very interesting to see how little Africa, South America and Australia have produced over the years. EU is responsible for a good deal, almost same as United States, but Asia is well ahead of us currently. And again, another interesting one which puts things into perspective. So this is the share of our CO2 emissions. So you can see somewhere, I think it was 1998, the crossover between America and Europe leading the charge with the amount of CO2 produced. That baton was handed to Asia, who are now well in front in terms of the amount of CO2 they produce per year. And it's all interesting to try and set the scene and really get you to understand the scale of the task that we face as a country and as a world. So this did tickle me though. If you look at these charts, you'll see that they all start back in 1750. Okay, they all start back in 1750. And back in 1750, the United Kingdom were the only people supposedly producing any CO2 emissions. The world emissions in 1750 was 9.35 million tons, all from the UK. So we led the charge, and I guess that comes back to the Industrial Revolution. I did some digging to understand how they established this, and it's based upon the amount of coal that was burnt in the UK in that year, or the amount of coal that was mined more appropriately. That's how they've established that figure. So not a great claim to fame, but we are recorded as being the starting point for CO2 emissions in the world. So if we zoom in on this graph a bit and we look at UK CO2 emissions, we are responsible for just under 1% of the world's emissions. So when you look at it on that graph there, we are a very, very, very small, well, under 1% of the world's emissions. So I'm not saying we don't need to do anything, we do, because we need to lead the charge. We've been the ones who've always been producing CO2. We've reaped the benefits from producing CO2, and so it's only right that we now lead the world into decarbonising our economy. But there's other countries that are going to have to act, and going to have to act in a significant manner to reach net zero as a world. As you can see, everything is going up. There's no real signs of it dropping at all. So we are 10% of the EU. We are equivalent to 30% of the world's transport emissions. So you see on the top there, that kind of beigey colour. That is world transport emissions, which is, getting on for 1 billion tonnes of emissions per year. You can read the rest of those. Some quite scary numbers. And this is just another infographic that puts it in another way. I quite like infographics to display information like this. They are, I find them easy to look at and get a good sense of scale. I think that's easier to understand than that is in a lot of ways when you look at the relative size of the boxes. Another interesting fact on CO2 is the emissions per capita. The average in the world is around 4.8 tonnes per person. That is the average amount of CO2 produced, so not an insubstantial amount. We are, as a country, we're at about 5.5 tonnes per person. France slightly less, and that's probably to do with their quite a lot of nuclear power plants over there. That probably helps quite a lot currently for them. Germany's almost double at 9.4, Russia 11.4, US is 15.5 tonnes of CO2 per person. Qatar is actually the leader with 37 tonnes per person. Not that you really want to win at that. Canada, interestingly, which I didn't think would even feature in here that highly, is about 18 tonnes per person. And the Falkland Islands, for some reason, at 16.9, but I'm guessing that's due to the small population and the requirements for heat over in the South Atlantic. So now we've been through all the doom and gloom. Well, we haven't been through all the doom and gloom, but we've just seen quite a lot of doom and gloom. There is good news. As a nation, our CO2 emissions per person is dropping. You would say there's a clear trend line there that back in the 1970s, 80s, we were at over 10, maybe 12 tons of CO2 per person per year. We're now dropping down, as I said, to 4.4, something around that. So that is good news. We are already on the right track. And a lot of that is due to removal of coal-fired power plants. We'll come on to that later on. And gentlemen, there you go, you can see it there. So most aspects of our life are fairly consistent. There's been a bit of a drop in industry between, what's that, probably 98 and 2000. A general decline in waste, CO2 consumed dealing with waste, and quite a steep drop off in CO2 produced from electricity and heat. Again, that's due to our charge into renewables when it comes to producing energy. So again, more good news. We are making a dent in the amount of CO2 that we produce as a nation. So we've all heard this net zero. I've got to say, before I started researching do this presentation, and believe it or not, I do some research before these presentations. I hadn't really looked at this document. I knew the general proposal and the idea behind it. However, I hadn't sat down and read, or I'm not claiming I read all this document, but I hadn't even skimmed this document to understand what's going on. So this was published in October 2021. And it is our strategy as a nation as to how we are going to build back greener and achieve net zero by 2050. Within there is this horrible graphic. And I mean horrible graphic. I don't know who produced this or what they were thinking. This shows how we're going to get to net zero by 2050, but for some reason they cut the graph off before 2050 and they only cover out to about 2037, which I still haven't got my head around as a concept. And then the colors all kind of blend into one, so you can't really tell what's going on and how it's going to happen. And I've got to say, I've become quite cynical reading some of these things, and I think that's probably a deliberate choice by the people who produced it, so they couldn't be held accountable for what the graph shows, because they don't really know. So they've made it so difficult to read that you can't follow it. So the point of this shows that we are going to transition to net zero, and we're going to do it by reducing emissions in all of our industries, though things like agriculture, they don't tend to drop off too much, but it does show we're also going to invest in offsetting. So in this dark blue down the bottom here, that is carbon capture and carbon offsetting. So we won't actually reach net zero by 2050, but we will when you take into account the offsetting and the carbon capture that we perform. So that's an important point to remember as well. We're not actually going to get to net zero, but our overall net contribution, well, I suppose it's in the world net zero, but I envisage that we were aiming for producing no CO2, but we're not. We're aiming to produce some CO2. We're just going to capture or offset it. And now saying it out loud, it seems obvious the word net is quite important in there. Interestingly, in the entire document, construction doesn't really get a mention. It gets passing references, but no real mention at all about construction and what we're going to do to achieve net zero, which is quite worrying, really, when you look at other government publications that talk about the built environment being responsible for 40% of emissions, but the government doesn't even feel the need to discuss it within this document. But it kind of shows the regard that the government has for construction sometimes. I think how many different construction ministers have we had in the past 10 years? I can't even count. So within this document, it goes in and it gives us a 9-point plan for how we are going to achieve net zero. I'm not going to go through all of these, but I have picked on one that is probably closest to most people's hearts, and one that you probably worry about, particularly at the moment with the cost of energy, is power. Where are we getting power from over the next, was it 30 odd years, 28 years? between now and 2050. So the key policies there, 2035, we will be powered by clean electricity. That is quite a big, meaty goal to put in there. They're investing in small nuclear reactors. I think we've all seen that in the news recently. And by the end of this Parliament term, they will have put in place a plan for another nuclear build, probably Sizewell, but yeah, probably Sizewell. But given that it's going to take over 10 years to get it built and operational, maybe more, because I think Hinkley started in 2018 and is due to generate in 2026. It's going to be some going to get Sizewell approved, designed and built and on stream producing power before 2035. But anyway, that's the goal that's been set. They're talking about 40 gigawatts of offshore wind, additional 40 gigawatts of offshore wind, I think of which we've already got 10 gig. So I think it's another 30 gig. But being the government, they present it as if it's all new. But when you dig down into detail, no, 30 gigawatts will be new. There's already 10 or 12 in place. More solar and other renewables. So they're quite woolly on what these other renewables are. Floating offshore wind as well, and the deployment of some sort of storage measures for power. Again, very woolly, no real discussion as to what that is, but some big plans there for us now. Again, I'm going off on a tangent here, but when I started looking at all this data and reading this report, I started to see where we are and how we get our power, and it's actually, hopefully you'll find it interesting. If you don't, well, unlucky. I found it interesting. So currently, this is the amount of power we produce so this is the last year, the amount of power we've produced through low CO2 sources. I say low because they're not measuring the embodied carbon within things like wind turbines or power plants at the moment. This is looking at, these are classed as clean because we don't count the carbon that's within the structure of the things that produces the power for us. So they currently produce power without giving off any CO2. That doesn't mean there's no CO2 used to build them, maintain them, and operate them. So around 5 to 6 gigawatts is nuclear, which is part of our base load. And then you can see the wind obviously varies with the wind speed. On a good day, we might be getting 10 gigawatts. But on a bad day, we might not even be getting, well, might get 1 gigawatt, but remember that won't be consistent. So wind alone will not work. We will need some way of storing the energy produced by wind. Yellow, obviously that's, well, not obviously, yellow is, sorry, I thought I had some explanations. Yellow is solar. Oh, it is there, right under my nose. So yellow is the solar power. Again, that really picks up April through to, looking at it, I don't know, September time, you'd say it's having an impact. But again, that's only going to be during the day. So you're going to be looking at needing some way of storing the energy we can produce through solar, whether that's local grids, i.e. houses who have solar panels and battery storage, or whether that's on a larger scale where we use sunlight during the day to pump water up to stored hydro. Who knows? But that's what we are going to have to be able to do to keep the lights on overnight. And hydro itself is dark blue. I don't know if that includes tidal or whether that is purely just hydro. Hydro is currently normally used as surge demand. So we have our base demand from nuclear and gas turbine or whatever else we use. And then if there's a peak that needs filling quickly, they can turn the hydro on and give us that extra kick of power. And by the way, this is, if you go to gridwatch.co.uk, you can see lots more interesting infographics about our power. You can even see what the grid is doing right at this moment in time, where our power is coming from, etc. It's quite a fascinating site to go on. Now, if this was the CO2 or the clean energy, I suppose, last year, this is all of our power. So you can see we're roughly looking somewhere between 30 to 38 gigawatts, drops off in the summer, picks up in the winter, as you kind of expect. The grey there is the nuclear. The orange there is gas turbine, blue is wind, yellow we've already been through. So gas is producing bloody great chunk of our power every day currently. The red line there represents the average that we managed to produce as clean energy last year. So we are making a reasonable dent. You would say it's around a third of our power demand last year came from renewable sources, which I've got to say, I didn't expect it to be that big when I started looking at this, and it's quite impressive, really. Going forward, there's obviously the government has within their net zero pledge, we will no longer be driving petrol or diesel powered cars from 2035. I think it's 2030 they won't be making, and more important, than 2035 they'll be gone, and we'll just be using electrically powered cars. So Ofgem thinks we need another 30% more power to achieve that. So that's not an insignificant amount of power we're going to have to find and be able to supply across the nation. But you've got to balance that with the fact that the idea of this net zero charge is we'll be using less power to run our homes, heat our homes, etc. So those two will balance out. But overall, I think Ofgem are forecasting a net increase in electrical demand, which brings more challenges to us. Not only have we got to decarbon or reduce the amount of carbon we use now, we've then got to find a way to make more power as well with carbon-free sources. So not necessarily a smooth ride. So they reckon it could be another 18 gigawatts to find between now and 2050. And just to put that in perspective, Hinkley Point is 3.2 gigawatts. So it's quite a few power stations to build. And bear in mind, you can't just build more and more nuclear power stations, because nuclear produces what we call our, didn't mean to do that. Where have I gone? Sorry, a nuclear is generally used for base load. Nuclear power stations, you can't ramp them up and down easily. They are on or they're off, and they run best at a certain range. So we would not generally, you wouldn't have a nuclear power station that's turned on and off during a day or anything like that. It would just run, and that produces our base. So that means the baseline is below the lowest point, that lowest power demand for our nation. So that can all be filled with nuclear, and then anything else has to be things that can be turned on and off fairly quickly. At the moment, we do it with gas turbines, or we have to find a way to store electricity. Now, if we can find a way to store electricity, then you can have more nuclear power stations in, charging up or storing in some way the excess power that they produce. That can then be brought back in overnight, say, or on the days when it's less windy. Anyway, so there's some big challenges ahead there. This guy, I don't know why I brought this back in. I think it's just to talk about there. So you're talking about gas turbines at the moment are producing a good chunk of our power. Some 9,000 tons per hour of CO2 is being pumped into the atmosphere when we're running our gas turbines currently. 8.966 kilotons per hour was the average last year. 9,000 tons per hour. I mean, that is 78 million tons per year. Is that right? Yeah, that's an awful lot of CO2 that's being produced from running gas turbines. And the sooner we can get rid of them, the better. Not just because of CO2, but because of a reliance on importing gas. And we all know what that means at the moment for all of our energy prices. So within the plan, they've set out these nice little graph that says this is what we're going to do each quarter, or each 5-year block, I think it is, sorry. Interestingly, it's only CO2 within our borders, as far as I can tell. Again, the government seems to be quite good at making documents that are woolly or hide exactly what you want to find out, which is what are we measuring, how are we measuring it. So it's not until 2035 that we even consider bunker fuel. So what they mean by that is when boats or planes land in the UK or come into a harbour and they refuel, that won't be included in our carbon figures. Interestingly, most countries are not including that at the moment. It might be a footnote, but it's not part of the CO2. It's not currently classed as CO2 emissions for a country, which is why it appeared separately on the graph at the very beginning. It's like everyone's saying, well, we all use it, so that can all just belong to the pool that is the world's CO2 emissions. Not sure that's right. And clearly by 2035, I think the government's going to start considering it. So probably the right thing to do. This, again, this is important to remember, this is not talking embodied carbon. We're talking purely carbon emissions, which is burning of fossil fuels effectively. So it's not even considering embodied carbon within things, which we'll come on to later. So, and I think this idea of embodied carbon is a deliberate thing from the government not to measure it, because for us as a nation to reach our goals, we are going to have to build a lot more infrastructure. And if we start measuring the embodied carbon within that and putting that against our targets, then that's going to push the targets. We're not going to meet the targets they've set. So the government is focusing purely on CO2 emissions, which I'm in two minds about this. Is that right? Is that wrong? It's better to do that we all transition to a position where our energy demands are being met by power sources that are net CO2 or CO2 negative or neutral. That's great. Do we need to then worry about the embodied carbon within the structures we build to achieve that? Probably. How we measure that is fairly interesting, which again we're coming on to. The bit that I really struggle with is measuring within our borders, just our borders. So that means anything that's manufactured abroad and imported, we don't have to worry about the CO2 emissions due to that. That to me doesn't seem right. And it's a bit like this. This is how it feels. We've done it. We've got net zero in our borders, but we're importing all of this stuff from around the world to achieve it. Is that right? I don't feel it is. Again, I've got no magic answer as to how we do it and how we would measure it, but it doesn't feel right to me that we're purely focusing on the emissions within our border. It opens things up to abuse. It means you're pushing people to import things rather than manufacture in the UK, because the CO2 emissions are lower. Excuse me, can you hear the dog bark in the background? No, you can't. Right, I'll carry on then. In fact, I'll let him in 2 seconds. Sorry, he was barking his head off at the door. I let him outside. It was a nice day, so there we go. Right, so that's the government's approach. There has been an awful lot of work done by all sorts of different people and groups within the UK to consider what this means and what we should be doing, what's the correct thing for us to be doing as a nation. Now, interestingly, this is a survey done by UK GBC, and I can't remember off the top of my head who UK GBC are. However, they've done a survey and they couldn't achieve a consensus on what we should be measuring and how we should be measuring a carbon balance. So some people, well, the minority were saying it's a worldwide thing, i.e. you can balance it across the nation. In fact, I think I've got the definitions here. So you can offset residual emissions throughout the world. Some are saying it has to be done within that one building. So they're saying that building itself should be net zero. That means that absolutely everything it consumes and what it puts out must be balanced within that one building. Some are saying it should be within a local authority borough. Some are saying it should be within the UK. So if you build a building, you operate it, as long as your carbon contributions within the UK are zero, then that's fine. Some are saying you should be able to balance it around the world. So for instance, you could build a building in the UK and you could offset it by planting trees in somewhere else in the world. Interesting, and shows that are probably part of the problem here, that we haven't actually reached a consensus on what net zero means. And this comes back to what I was talking about. Is it within our borders, or is it within the world's borders? Anyway, interesting and plenty hopefully to make you think. So let's get back a little bit towards where this was supposed to be headed, which was construction. Well, it's supposed to be temporary works, but importantly, construction. So I'd seen a lot of these headlines before. Construction industry accounts for 38% of CO2 emissions. That was a headline on the Environmental Journal's webpage. And I thought, bloody hell, that's quite some output. And then you start digging. That's not what it means at all. They're talking about the built environment as a whole, not construction by itself. So two entirely different things in my mind. And then you do some more digging. And what you actually find is this: the built environment is responsible for 40%, and the construction sector contributes 11%. Now that 11% is actually a global average. It's not a UK-based average at all, as far as I can tell from the references within here. And it also includes transport for some reason. So transport is being lumped into the built environment. So that 40% figure includes all of the cars, trains, everything within the UK that is classed as transport. So a very, very misleading headline. So what are we actually responsible for directly? Construction. This is from ONS data, I believe. And there you go. That's the UK's greenhouse gas emissions. Now this one, the only one I could find was carbon dioxide equivalents. So this is CO2 equivalent. This isn't just CO2. So that's why we've actually got quite a lot more if you add all those up than the figures at the front end showed, because it's the equivalent. So looking in here, manufacturing and construction is responsible for 31 out of almost 500 million tonnes, 500 million tonnes of CO2 equivalents we produce each year. So construction and manufacturing is 6.5, near enough 6.4% of the UK's CO2 emissions. Okay, quite different to the 40% we saw at the front end there. Then we go to another website which claims to be using ONS data as well, and they have a different story to tell. So they're saying 12,500 tonnes per year comes from CO2, but this one I think might just be measuring CO2 rather than equivalents. So it's actually somewhere between 3.8 and 4.1% is construction related rather than construction and manufacturing. So you can see here that we've got data that's all supposedly from the same place. So then I found where this actually all comes from, which is something called the Blue Book, not the Blue Book that we all know as engineers, but the Blue Book as in the country's accounts, which again, I didn't really know there was such a thing till I went digging and looking at all of this. Within the country's accounts, they look at CO2 emissions. And in there, we have construction as 13,500. That must be 13.5. I've cropped it off there. What are the units here? Yeah, so that's 13.5 million tonnes, isn't it? It's 13.5 million tonnes from construction. And this is based on classification of businesses based on SIC codes, which is your classification as a business that you use for a number of things when you're doing your HMRC, when you're registering your business, all these things. So that's what this is based on. And you can see there, they're looking at 13.5 million tonnes. What I'm not sure of is, or what I think is that this is purely the CO2 emissions from people working and building things. I don't think it includes all of the materials, etc., that are used to build a building and the production of those, because I think that would be covered under the manufacturing section up here. But again, it's fairly difficult to figure out what's going on. So if you put that on a bar chart, not a bar chart, try again, a pie chart, that is construction emissions within the UK. So, or if you're looking at it in the world, we're about 0.039%. Or in the UK, we are about, I'll put it somewhere. I think it's about 3 or 4% anyway. And that's the breakdown of those emissions. So building and building works, construction and construction works, and specialist construction works. Quite what those mean, I'm not entirely sure, but that is the breakdown of how we get to our figure. Yeah, so yes, 2.9% of the UK's CO2 emissions is from construction work. 0.039. So we've just established that construction only accounts for somewhere between 2.9 and 4% of UK emissions. So why are we worried about that? Firstly, the reason is because we've got to do something If everyone does something, things get bigger. If we all go, oh, we're only responsible for a little bit, someone else will deal with it, then we don't get anywhere. Okay. But construction and the broader building construction industry are responsible for an awful lot more than those emissions, as in we have control over a lot more. By our very nature, we get involved with infrastructure and housing and schools, hospitals, everything. And we have the ability to influence those buildings and how energy efficient they are in the future, what they're made of, the embodied carbon within them, how they can be taken apart, what will happen to them when they're demolished. All of these things are in the control of us as an industry. Now, back in 2010, the Department for Business, Innovation and Skills put out this report. And I've gone back to this one because it was the last government-based document I could find that even talked about the situation. And you'll see here, again, we're talking about emissions only. So, excuse me, the emissions from design through to assembly on site, not massive. In use is where the bigger picture, and still is the big picture. It's here where we're going to save our CO2 emissions and make a big dent. And construction is going to have to play a big part in that. That means speccing up buildings so they are using the minimum amount of power, designing in or insisting that people put in solar panels and heat source pumps, all these things to produce your heat and your power locally with no emissions. That is what we're going to have to do. And that's what they mean when they say we can influence an awful lot of CO2 emissions. So that is where we're coming from. And again, breaking it down further, this is where the emissions were. And this was the last document I could find that even tried to show where these emissions come from during the building process. And this is a document from 2010, was the last thing the government produced on this subject. And I don't think it necessarily holds true right now, but anyway. So you can see that the actual construction of the building is a small part of the pie there. And this one's more for interest. So this is where the emissions are coming from. You can see there, so clay products, cement, lime and plaster is 11.6 million tonnes of manufacturing back in 2010, which I think was based on 2008 figures from memory. Maybe even though they go, imported construction products in 2004 was almost 16 million tonnes of CO2. Again, where's that being measured now? Is it being measured? Should we be measuring it? A more up-to-date one, and this is now talking about total, so equivalent CO2 rather than just CO2. And this is a document by that's a few people: GBC, World Green Building Council, Building Life, Lord Foundation, and the IKEA Foundation. This document, quite a good document. Again, some nice clear graphics in there that gave me a good understanding of the problem we face. So they're claiming the total UK emissions is 703 million tonnes. So they're taking into account consumption base, which means the stuff outside of borders as well. And they're saying within our borders is 539. So you can see there's a good, not far short of 200 million tonnes of imported CO2 that the government's not currently tracking. And what they're suggesting there is that there's 292 million tonnes that we can influence as the built environment, and 177 million tonnes that we directly control. So this is where the industry is going to make these changes that's going to save this carbon. We have the ability to affect this and to directly control this. Now we come on to what I've talked about a few times already: embodied carbon versus CO2 emissions. So emissions relates directly to burning fossil fuels, generally burning fossil fuels. Embodied carbon is the carbon that is effectively within something. So as an example, a brick. So to calculate the embodied carbon, you'd have to calculate or measure the carbon from quarrying the raw material, the energy used to make the brick, the energy used transporting it, and the energy used to lay the brick within a building. That was how you'd quantify your embodied carbon. Okay. Again, if it was manufactured outside the UK and shipped in, all you would have to take into account would be, well, theoretically, we'd have to take into account is the transport and the laying of it on your site. Is that right? Probably not. And looking at it, the iStruct don't believe it's correct either, because their documentation, and in fact, a lot of the guidance for calculating embodied carbon says you must take into account where it's come from and where it's been manufactured. If you don't know exactly, there's assumptions that you can make, and they've given examples within their documents. So the government might not be recognising it or choosing not to recognise it, but our industry bodies are, which again I think is the right decision. The only question that I struggle with is, if we're measuring the CO2 emissions of producing that through the manufacturing, right, we then count the embodied carbon of that brick within the embodied carbon calculations for a building. Are we double counting it? I haven't really got my head around the answer to that. And if somebody knows the answer, that would be brilliant. If you're in the end of the Q&A and we can run through that, it'd be great, because I couldn't quite get my head around how we measure and how we tell the difference currently. The reason embodied carbon matters, okay, so if we look at a current building, the embodied carbon and the construction is only about 16%. But as these buildings become more efficient, i.e. we use less energy or we use greener sources of energy, the amount of embodied carbon within a structure becomes a far bigger slice of the action, which is why we need to focus on how we reduce that embodied carbon. At the moment, it's a small slice, but it becomes a much bigger slice as the building becomes more efficient. And again, maintenance and renewal of parts of the structure becomes a bigger slice. So they're all things that need to be looked at. Structural engineers, Institution of Structural Engineers, how to calculate embodied carbon. Brilliant document, very interesting. As I said, I'm not sure how we avoid this double counting. Well, you're counting it in the embodied, but you're also counting it in the national emissions. And as we transition to green energy, our emissions will drop off, and therefore so does the embodied carbon within. If you make a brick using clean power sources and you transport it using clean power sources, the embodied CO2 within it is smaller. So by dealing with the energy, surely we deal with the embodied carbon effect. But maybe I'm oversimplifying it, or I'm missing something here, but that's where I'm at the moment. So they're suggesting that 50% of the embodied carbon comes from raw material, transport, manufacturing. Then you've got 4% of transport, and then you've got I think that's 1%, yeah, 1% of construction installation process. So it's not a great deal of embodied carbon within the construction process or within the emissions either, when you look at our emissions as a country. Use of the building, 20 to 23%, end of life, 2% now. This is all geared up towards building buildings, and this that's what I'm looking for, circular economy. So at the end of a building's life, it can be taken apart and it can be reused. That automatically reduces the carbon cost of the building because it's being used again. There's lots and lots of guidance out there on this, so I'm just scratching the surface here, just giving you a bit of a whistle-stop tour of where I've got to and what I found in my research. So brilliant document in the LETI, which is London something or other Climate Emergency Design Guidance, where they're looking at embodied carbon within structures, and it gives examples of the amount and where it is. So for a small scale housing, 80% of it is within the materials. 14% is 14% is within. That's pointing the wrong thing. It should be pointing at that 1%. Sorry, that 14% is maintenance replacement. 1% or less than 1% of the embodied carbon is in the construction process itself. Medium large scale housing, we're up to about 2% within the construction process. Again, you can see the figures yourself there. I'm not going to read them all out, but it was interesting to see people actually taking the time to put these down on paper so you can understand what this means and the amount of carbon, embodied carbon within the structure. and even breaking it down from superstructure, substructure, finishes, facade, MEP, commercial offices as well. Interestingly, it's almost a 50-50 split between the construction and maintenance and replacement. And that's probably because offices are recycled and reused, so there's more change of a building over its lifespan. Similarly for schools, a great source of information to understand embodied carbon and where it is in structures and where to focus your efforts as well. So embodied CO2 and CO2 emissions related to construction, i.e. the actual act of building, are a small part of the emissions, 2% embodied CO2, 4% of CO2 emissions. That means the temporary works plays a very, very small role in both embodied CO2 and CO2 emissions. On that basis, to my mind, it's not the place to focus our attention to try and solve this issue, this global issue. Much bigger issues to solve as a nation before we worry too much about temporary works, which is probably why the I-struct-T don't even consider. So you see the green box is the bits you must measure if you're doing embodied carbon calculations. Temporary works is in the grey box here and doesn't even form part of the scope, the required scope at the moment, because it's quite a small part of a project. There's always going to be exceptions to that. As we all know, some projects are very, very temporary works heavy. And does that mean we should do nothing? No, it doesn't. I'm not suggesting we should do nothing, but what I am saying is we're not going to save the planet by reducing the CO2 in temporary works. There's no way that's going to make enough of an impact. But what can we do? And what are we doing? Good design, using the minimum amount of materials while keeping the temporary works as robust as we need them. That's great. Because if you need temporary works, you need temporary works, and then you've got to make them safe. So there's no ifs and buts with that. Proprietary material, guidance note from the TWF on proprietary materials and CO2 emissions. It's a good example of the circular economy. They go out to site, they're used, and then they leave the site. Go to another site, they're used. It's brilliant. That's exactly what we should be trying to do. Whenever we can, we will design with proprietary products, unless there's a good reason not to, such as it's going to stay in place for 4 years or whatever it may be. Avoid import and export of materials on sites. Try and reuse materials from previous schemes. A lot of our clients hold a stock of suitable materials. It used to be more common than it is. With the current drive towards a cost for each project, that drive to kind of save, reuse and move materials between sites has probably dropped off a little bit, I would say. Consider sustainability in our designs directly. Use improved site one materials. So certainly for us, we now actually have a section on sustainability directly within all of the reports we produce for temporary works designs. Sometimes it's a one-liner like that, sometimes there's a bit more to it, but this came about from discussions we had last year. In fact, I think it was Josh's idea to include this in our reports now, so we are actually thinking about it as a business. Eliminate temporary works wherever possible. It's always been great advice. If you can get rid of them, that's good. Load testing to demonstrate the capacity of the structure. Now, whether that's in a temporary condition or even in the permanent condition, there are companies out there like Swan Test who will do large-scale load testing on structures to demonstrate the capacity. Spending more time on analysis and SI. If you can demonstrate the structure works without temporary works, then that's great. You've eliminated the need for the temporary works. You might spend more time and money on the analysis, but you eliminate the temporary works, and therefore you eliminate the CO2 emissions and embodied carbon associated with that. Look at tweaks to the permanent works that eliminate temporary works. Again, if you can add a small amount of extra rebar or a small extra beam into the permanent structure that reduces, or even just resequencing the works that reduces the need for temporary works, that's a big win. Again, you've lost that CO2. Keep learning. Again, this has been an interesting learning curve for me, understanding CO2 and what it means to us and where the big wins are in terms of reducing it. It's been interesting. Should we be measuring carbon in temporary works? To be perfectly honest, I'm not convinced it's worth the effort. I think if we focus on these things up here, then that's probably a better solution than spending a lot of time measuring carbon, unless there's a very, very quick, efficient way of doing it. I don't think we're going to, as I said, we're going to save the world by saving carbon in temporary works. But these principles and always thinking about it is going to help us. So what's already being done out there? So Keltbray and Wentworth House, this earth-friendly concrete, which I believe doesn't contain any cement at all, which is always a plus. Cement accounts for a good chunk, around 6% of worldwide emissions, I think it is comes from cement production. So it's a big win if we can start dropping out the amount of cement within a structure. Things like research papers like this one from the Temporary Works Forum, thrust blocks. If we can do research and demonstrate we don't need thrust blocks that are that big, then that's great. It means we reduce the amount of concrete and therefore the amount of CO2 that we're using on a site in the temporary condition. This is an interesting document, protocol for reusing structural steel, which covers exactly what it would sound like there, recovering steel from structures and then looking at using it again. Brilliant, great idea. I know there's many practices in the UK that are already looking at this and how it's going to be dealt with. There's challenges to be overcome, but if we start, we can get going, can't we? Permanent works designers, there's loads and loads of guidance notes out there for you on what you can do, how you can do it, etc. All right, and after 55 minutes of me yapping away, it's now time for Josh to have a go, and he's just going to do a little case study for us on how we can and how we have cut down on CO2 emissions in temporary works design. Over to you, Josh.
Oh, that was seamless. I was going to do some quick filling. I'm just going to say that I'm disappointed. I'd already updated my LinkedIn to say that I was saving the world, and now I'm going to have to change that back. So on that bombshell, I'll hand over to Josh.
Would you mind? Could I share my screen, Angus?
Yeah.
So whilst they do that, I will just remind everyone that if you've not got anything planned for the weekend or you've got some time, we have more than 50 hours of temporary work CPD webinars now on our YouTube channel, all part of our plan to make Angus a YouTube influencer. So I'll put the link in there should you want to do that. And always get asked, this webinar is being recorded, as all of them are, and the presentation sections, with the exception of any Q&A, which we always stop the recording to allow a more, should we say, frank discussion, will be made available Monday or Tuesday next week. So over to you, Josh.
Thank you very much, Christian and Angus. So what I'm going to do is get my magnifying glass out and start looking at a particular project. What we've covered so far is construction industry and some typical practices, but we're going to focus on a particular project where we've looked at the sustainability of a couple of alternatives to a standard pure granular crush pilot platform. So this case study is going to be based on Sugar House Island development, which is in East London in Stratford. And the developer is Vastint, and our client was John F. Hunt Remediation, whose scope of works was to provide the site remediation, the working platforms, and there was lots of various other items of temporary works throughout the life of the project, which is still in progress. But John F. Hunt have finished their portion of the work, and with their operations having started back in 2014 or so. But the general project was developing a large brownfield site into a mixed-use development, and the site extent is shown here. It's quite a large site covering lots of different areas and lots of different developments, but we're going to look at one part of it. We can see the plan area of the site here, and showing the different blocks of development. There were many platforms that were used as pile mats over these blocks. All different types of piling were required for the different types of buildings. So we had different pieces of plant and different methodologies required. But the pile mats that were required for each area, with the general purpose of those was to provide a safe and durable working surface from which pile rigs can operate. And there was generally three main types of platform, of which we used all three on this project, requiring different purposes. But we've generally got a pure crush mat, which is just pure recycled 6F2 or something similar, type 1 or something. That's just unreinforced. Then we've got a Geogrid reinforced mat, which has got the Geogrid in there in layers, which strengthen the mat and enable it to provide additional load spread, therefore reduce the thickness of the mat. And then finally, we've got a stabilized mat, chemically stabilized mat. Each have their own pros and cons, and the pros and cons for selecting each type varies really from site to site. For more information on these working platforms and their construction and design philosophies and maintenance and some general top tips, we are going to be hosting a full webinar on this subject next month. So if you're interested in how your working platforms can perform better for you, then that's well worth tuning in for. But for now, we're going to focus on the kind of sustainability of these alternatives. So to showcase this potential sustainable benefits from this alternative mat construction, I'm going to take one mat design out of this whole area. And on this particular area, we provided an option for all three types, depending on what the contractor was wanting to do with that particular site. The rig used was a medium to large kind of scale in terms of its size, and the ground conditions were soft clay, and there was also a very high water table. So there were quite tricky ground conditions to contend with. The solutions that we provided are illustrated here. So we've got the pure crush option was a 925 deep pure crush mat, which is quite deep as most mats go. That was a direct output from the pure ground conditions that we had, so we had to have a deep mat. The next one is the Geogrid reinforced platform that's got 2 layers of Geogrid in there, and that was 600 mil deep. And then the final one is a composite mat, and that's constructed from 600 mil deep of stabilized soil, which was the in situ soil stabilized with 4% ordinary Portland cement, or OPC. And then this stabilized soil had a 150 mil layer of crush on top. And in all these instances, we had a geotextile provided beneath the crush layers, just to provide that fines migration control into the upper mat, and also act as a marker layer too. So we're now going to look at how these designs compare to one another. And this review is based on several assumptions: that the 6F2 material is recycled and imported locally from a site. It's not traveled too far. Also, that the cement and the Geogrid used are sourced within the UK. And we're also assuming that the working platform is going to be retained on site to facilitate the follow-on trades, scaffold bases and things like that, and providing a bearing level for the new structural slab. So it may be that they'd need to scrape off the top layer that's contaminated, but that's typically done on pile mats anyway. So if we look at the savings that these could provide, these two solutions, alternative solutions to that pure crush mat can provide. If we look at the Geogrid first, we've got a 35% reduction in thickness. That leads to an approximate cost reduction of 22%, taking into account the less material usage, but you've also got the Geogrid on there as well. And then based on some approximate carbon footprint figures from the manufacturer, this comes to around about a carbon footprint reduction of 38%. It is, of course, very difficult to calculate this carbon footprint, but these can give you some kind of ballpark figures. And the next one is the stabilized. So we've got a 19 reduction in the overall thickness, but remember that the stabilized part of this mat is mostly made from the existing soil that was already there on the site, with a small percentage of cement. For these kind of mats, that's typically less than 6%. So therefore, we've got an approximate 80% reduction of materials that have been brought onto site, which is the cement and the 6F2 material, which is used as a granular wearing course on top. So that's a vast reduction on the other types, but, and it's quite a big but really, we are using cement in this stabilization process, which in itself consumes a lot of carbon during the manufacturing process, as we've been hearing from Angus. So these points take us to an approximate carbon reduction that varies quite wildly depending on the calculator that you use and its assumptions. Some sources quote that it's about 45 kg per meter squared of that map for this thickness. But again, this varies, and from my rough calculations, it kind of brings it between the pure granular and the Geogrid types. And this value engineering and provision of alternative mat constructions kind of boils down to really a reduced overall mat depth, which therefore limits the removal of the soil on site to get down to reduced dig levels, and then the limited import of materials, which is all leading to that reduction of carbon consumption. And to summarize, that reduced overall mat depth, limited muck away, and limited import material leads to reduced use of natural materials and resources, less transportation of materials, and also faster construction time. And all these have clear benefits on reducing carbon emissions and assist, however little that may be, on reaching our net zero emissions target. But in addition to this as well, are there any other benefits to consider when we look at the total pictures of sustainability, or what we call the 3 pillars of sustainability? Because ultimately, sustainability is providing the needs for today without compromising the ability for providing tomorrow's needs. And this is the fundamental value on what net zero agenda is trying to achieve. And it's worth noting other benefits that are essential of part of being sustainable, and these can be tangible benefits such as creating a better environment and economic stability, in which we've already kind of discussed, but there's also those non-tangible benefits such as reduced transport movements through a community and faster construction time that both have a positive social effect on that local community. How you measure and compare that, very with great difficulty really. And then to throw this on its head, it may be more sustainable to provide a deep pure crush mat in the right circumstances. Say if you're on a site where the formation level needs to be raised up and you've just demolished a very large RC frame structure on that same site, then you can keep that same material on site and provide that crush. So it really is very site specific, and therefore the approach to effective and sustainable construction is really exercising that muscle between your ears and using your noodle, thinking about decisions carefully and site specific and your site constraints and what you're trying to achieve and the drivers for your specific project. Working harder and not smarter. Sorry, working smarter and not harder. Don't get that the wrong way around. Working smarter and not harder, and improving that built environment by leaving it a better place than what we started with. So that's just a really quick drill down into a specific project, which hopefully kind of compounds those lessons that we've been discussing. There's many a document which Angus has perused throughout his research on the subject, some of which are listed here. And Angus, are there any that you want to cherry pick?
Oh, I mean, if you found it interesting or you want to learn more, there is, I said, there's an awful lot out there. You can have a look at the net zero strategy and see how convinced you are by it. I mean, they're trying to do something, I suppose, but I wasn't overly convinced by some of the strategies in there. There's some brilliant documents. The Letty ones were good. The iStruct ones on embodied carbon, and there's the free as long as you register carbon calculator they have, which is good. These ones this is the one, the net zero whole life carbon roadmap, interesting as well. The low carbon construction, quite an old document now, but still interesting. And the one on the consultation for a UK GBC was the one that has surveys and trying to understand what people understand by the concept and trying to agree a definition of what we mean and what we're trying to achieve. So yeah, there's some interesting stuff, and I think every engineer should be reading and understanding what we're doing and how we're going to get there, because it's not going to happen if we don't try and do something, that's for sure.
We've got some upcoming webinars in April, end of next month. We've got a kind of a working platforms based webinar. And then in May, we've got a temporary works procedural control with Ray Phillip too. They are just the ones that are under our feet that are coming at the moment. There will be more to come. And finally, that concludes our webinar today in terms of the content that we're going to present. We will be taking questions very shortly. So please, if any questions do spring to